Two materials can look almost identical. Same thickness, same wall. But one lets water vapor pass almost freely, while the other resists it hundreds of times more. The number that reveals the difference is mu. Mu is the vapor diffusion resistance factor. It compares a material with still air of the same thickness. If mu equals 1, the material resists vapor about as much as air. If mu equals 10, it resists vapor 10 times more. Think of mu as a traffic slowdown for vapor molecules. Air is the baseline. A low mu material slows them only a little. A high mu material creates much more resistance. But mu does not mean vapor stops. Why do materials differ? Their internal structure. Open, porous materials offer easier pathways. Dense or vapor control materials create more resistance. Mineral wool is usually low mu. Dense layers are often higher mu. Compare equal thickness samples. A mineral wool block, a wood fiber board, and a vapor control sheet, all measured at the same depth. Each shows a different mu. But mu alone does not tell the resistance of a real wall layer. To describe a real installed layer, mu must be combined with thickness. Multiply mu by d, the material thickness in meters. The result is SD, the equivalent air layer thickness in meters. This is covered in the next note. A high mu value does not automatically make a material a vapor barrier in a specific wall. A thin, high mu layer may have less total resistance than a thick, lower mu layer. Installed thickness matters. A low mu value does not mean bad or leaky. It means lower resistance to vapor diffusion through the material. It says nothing about airtightness, insulation, structural capacity, or liquid water resistance. Mu concerns molecular vapor diffusion through the body of the material. It does not measure air leakage through joints, holes, seams, or pore installation. Airtightness and vapor diffusion resistance are separate properties. Declared mu values may appear as a range rather than a single number. Some materials change resistance with moisture content or test direction. Design calculations should use declared product data and applicable local requirements. Comparing mu values only makes sense when layers have the same thickness. For real installed layers with different thicknesses, use SD value. Mu is one input into building physics, not a standalone safety rating.
Key takeaways. Mu is a dimensionless ratio compared to still air. Higher mu means greater diffusion resistance. Mu alone does not describe a wall. Combine mu with thickness to get SD and see node C02-013 next.